So let's discuss about some applications of Gauss law today in this class. So the first application of Gauss law is electric field. Electric field due to an infinitely long line charge. CHARG. Okay? Electric field due to an infinitely long line charge. In the previous class, we have studied about Gauss theorem. And the Gauss theorem says like this, okay? Let us recall Gauss theorem, Gauss law, just the definition. Suppose there is any closed surface, suppose this is a sphere is a closed surface, and this closed surface encloses a charge Q at its center, no? Then the total electric flux through this closed surface over the entire closed surface will be given by what? 1 by epsilon naught times the charge enclosed by the sphere. Okay? By this closed surface. This sphere is a closed surface, right? Sphere, it has a closed surface. It encloses a charge Q, suppose. Okay, a charge Q is situated at the center. Then Gauss law says that the total electric flux over the entire surface of this sphere, over the entire closed surface, is given by 1 by epsilon naught times the charge enclosed by this surface. Is it okay? Yes. Or, in other words, Gauss law also says that this expression can also be rewritten as integration of E dot ds. Integration of E dot ds means electric field over the entire surface of the sphere. Okay? Electric field over the entire surface of the sphere is given by 1 upon epsilon naught times the charge enclosed by the sphere. And since this is a closed surface, this is how we write. That is how we write, right? Yes. Is it okay? No? So this, in the last class, this is how we have discussed Gauss theorem. The total electric flux over the entire closed surface is given by 1 by epsilon naught times the charge enclosed, or the electric field over the entire closed surface is given by 1 by epsilon naught times the charge enclosed. So we are going to use these two relations. So let us keep in mind that phi is equal to 1 by epsilon naught times Q, and then integration of E dot ds means the electric field over the entire surface, entire closed surface, is 1 by epsilon naught times. Is it okay with you? This is just recalling, okay? So using Gauss theorem, Gauss law, I'm going to derive the electric field due to an infinitely long line charge. So you have an infinitely long line charge. Is it okay? So you have an infinitely long line charge. This is an infinitely long line charge. and let lambda be the surface or be the linear charge density. Okay, linear charge density. So consider an infinitely long straight line charge having linear charge density lambda. Now, okay, suppose you consider any point P here at some distance from this line charge, and I want to find out what is the electric field at this point due to this line charge. Okay, so in that case we need to apply Gauss law over here. So in order to find not only here, you can find out the electric field at any point, okay, around this line charge. You can find it anywhere. I have chosen one such point P. So in order to find out the electric field at this point P, which is at a distance r from the line charge, is it okay? Yes. What do we need to do is, we need to draw a Gaussian surface around this point P. What do we need to do? We need to draw a Gaussian surface. And what is a Gaussian surface? Last class we have discussed. Gaussian surface means it is a surface, a closed surface, which should be symmetric about this charge. Gaussian surface means it's a surface which is symmetric about a given charge. Suppose you have to draw that surface around this point P. Okay? So that, okay, the distance at any point on the surface remains constant to this line charge. Means you need to draw such a surface, you need to draw such a closed surface so that the distance, okay, distance of the line charge, distance from the line charge to the surface will always remain the same. Is it okay? See? Yeah. So you need to draw a surface, Gaussian surface, such that the surface remains symmetric about the given charge. The charge, okay? The surface should be symmetric about the given charge. So symmetric. And another thing is that this surface, the electric field at every point on that surface should be same. So electric field must be same. Must be same. So what you need to do is, in order to determine the electric field at this point P, you need to draw a surface, a closed surface, we call it as Gaussian surface, such that that surface, it should be symmetric about the given charge, okay, about the given charge. And then the electric field at every point on that surface must be same. Is it okay? So let us draw a Gaussian surface, okay, show this, where point P lies on that surface. Okay, we have to draw a Gaussian surface such that point P should lie on that surface. So in order to do that, we draw a cylinder. In order to do that, what do we have to do? We need to draw a cylinder of radius r. Only then the point P will lie on its surface. Okay? So let us draw a cylinder of radius r. So if we draw a cylinder of radius r, I think this is how it should look like now. See? See? Okay? So in order to find out the electric field at this point P, okay, due to this line charge, what we have done is we have drawn a Gaussian surface, a surface which is symmetric about the given charge. and the electric field at every point on this surface must be same. Is it okay? So this is how we need to draw the Gaussian surface. Now, sabido, how is it symmetric about the given charge? You take any point on its curved surface, okay? You take any point on its curved surface. Then the distance of that point from the line, from this line charge, will always be same, will always remain constant. Okay? You take any point, ito Gaussian surface ba na siya? You take any point on the surface, on its curved surface. Then the electric field, or then the distance, okay, from the charge will always remain constant. Okay? Yes. Suppose if you take this point P on the surface, then this distance will also be R. If you take this any point here on the surface, then this distance will also be R. And at every point on the surface, the electric field must be same. That means electric field at this point, electric field at this point, electric field at this point. No matter wherever you take a point on the surface, the electric field should always be same. That is Gaussian surface. Okay? So it's very simple, no? No, it's very simple. Let me just highlight you again. So we have we have an infinitely long line charge, right? We have an infinitely long line charge having linear charge density lambda, right? We have the linear charge density as lambda, and we want to find out the electric field at any point PC, okay, which is at a distance r from the line charge. So in order to find out the electric field at this point, what did we do? We drew a Gaussian surface such that the surface should be symmetric about the charge. Alright? Yes. And the electric field at every point on that surface must be same. So in order to draw a Gaussian surface, we need to draw a cylinder of radius r such that the point P lies on its curved surface. Is it clear to you? Okay. P is here, okay? Is it all right? Yes. Okay. Now, the total electric flux over this surface, now, here, if we consider this Gaussian surface, this closed surface, then we have three surfaces. This cylinder is divided into three surfaces. This is your first surface, now, surface 1, ne? This is another surface, right? This is your surface 2, and this is your third surface. Is it okay? So the electric flux, the total electric flux over this entire Gaussian surface will be sum of the electric flux at surface 1 plus sum of the electric flux at surface 2 plus sum of the electric flux at surface 3. So sum of the electric flux over these three surfaces will give you the total electric flux over this entire Gaussian surface. See, what I'm doing is I want to find out what is the total electric flux over this entire surface, right? Then see, this cylinder has three surfaces. One is your upper base. Now, upper base cylinder has an upper base, right? It has two bases, right? So this base, which is your first surface. Next one is cylinder has two bases, so the lower base, right? Which is your second surface. And the third surface is your if this is a cylinder, This is your area of base, which we considered as the first surface. This is also another surface, area of base, which we have considered as the second surface. What is another surface? In class 10 you have learned. When you curved surface area, this is your curved surface area, right? So that is your third surface. So the total electric flux over this entire Gaussian surface will be the sum of the electric flux over this surface 1, over the surface 2, as well as over the surface 3. So that will be phi 1 plus phi 2 plus phi 3. Correct? Yes. According to the definition, phi means what? Phi means phi. Phi can be okay, from suppose C. According to Gauss law, the total electric flux over any closed surface is given by what? 1 by epsilon naught times the charge enclosed by the surface, right? Also, in another form, the total electric flux over any closed surface is given by the total electric field over that surface. Is it okay? Shall we combine these two? Since it's closed surface, so I use like this one in integration. So shall we combine? After combining, then integration of E dot ds will be equal to 1 by epsilon naught times phi. Is it okay? So this is also Gauss law. Any one of this is Gauss law. This is Gauss law, this is Gauss law, this is Gauss law. Okay. So see, electric field, total electric field over this surface 1 will be given by what? Electric field over this surface. Electric field over this surface 1 will be given by, or you can say electric flux over this surface 1. Electric field over this surface 1. Electric flux over this surface will be given by what? Electric flux over this surface 1 will be given by what? Integration of E dot ds, right? Electric flux over this surface 2 will also be given by definition E dot ds. Electric flux over this surface 3 will also be given by E dot ds. Now very, very important step is coming up. Okay, very, very important step is coming up. Now see, this line carries a positive charge, and for a positive charge, what is the direction of the electric field?
Radially outwards.
Radially outwards. Radially outwards. Electric field acts radially outwards, right? So electric field acts radially outwards like this. This is your electric field, correct? Now, for this surface, what is the area vector? What is the direction of area vector? Area vector means it's always perpendicular. Area vector is always perpendicular to the plane it contains, right? Is it okay? Yes. So what will be the area vector of this surface? What will be the area vector of this surface? Of this surface 1? What will be the area vector of this surface 1? In which direction is the area vector for this surface? What will be the direction of the area vector of this surface? For this surface, what will be the area vector? Area vector means it's always perpendicular to the plane it contains. No? So what will be the area vector of this surface? Suppose you have a circle line on the table. Okay, what will be the area vector of that circle?
Vector R.
what will be the area vector of that surface, of that circle? You have a circle lying on the table. Is it okay? Suppose, just think that this is a cuboid, or this is a closed surface, right? A closed surface. Consider the top face. Consider only the top surface. Then what will be the direction of the area vector? Area vector will be what? In this direction, right? Area vector will be in this direction, perpendicular upwards. Is it okay? Perpendicular outwards. For a closed surface, it cannot be perpendicular downwards for this top surface, right? Is it okay? Yes. But if you have a circle, then the area vector will be either perpendicular up. If you have a circle in this plane, in xz plane, suppose this is your x-axis, this is your y-axis, this is your z-axis. If you have a circle in xz plane, then your area vector will be either perpendicular upwards, that is acting along positive y, or it will be either perpendicular downwards, that is negative y-axis, right? For open surface, right? But closed surface, the area vector is always perpendicular outwards. Okay? Yes. So for this surface, what will be the area vector? In which direction?
Perpendicular outwards.
Yeah, perpendicular outwards means so this will be the area vector, right? So it will be perpendicular to your electric field. Is it okay? Yes. For this surface, also see electric field is acting radially outwards in this direction, right? No? Arrow, what will be the area vector for this surface too?
Perpendicular outwards.
Perpendicular outwards, so in this direction. No? So just think that this circle is like this. So the area vector will be perpendicular in this direction, right? That means this is your area vector. So area vector and electric field, they are making an angle of 90 degrees. Is it okay? And then for this curved surface, see, electric field is in this direction, right? Electric field is in this direction. Okay? Yes. And for this surface, see, electric field is in this direction. Now for this closed surface, for this curved surface area, what will be the direction of the area vector? The area vector will also be like this, right? See, for this curved surface, suppose just consider a point P on that surface, then the area vector will be in this direction. For this surface, this is your area vector. Is it okay? That means for the curved surface area, the area vector and the electric field E are in the same direction. Now, the area vector and the electric field are in the same direction. In the same direction. So the angle between them will be 0 degree. Are you following that? The angle between them will be 0 degree. So you know that dot product of two vectors A and B is given by magnitude of A, magnitude of B, with the cos of the angle between them, right? Here also see, dot product of two vectors, right, is given by what? Magnitude of E, magnitude of ds, the surface, and cos of the angle between them. For surface one, what is the angle between
90 degree.
Electric field and the area? 90 degree. For the second surface also the same thing. Angle between electric field and the area vector is 90 degree, so cos 90 degree. But for the third surface,
0 degree.
the angle is 0 degree, so cos 0 degree. Are you following that? Cos 90 is 0. So E dot ds into 0 is 0. So this is 0. Cos 90 is 0. Also E into ds times cos 90 is 0. So 0. Plus here, it will be simply E ds because cos 0 is 1. So your total electric flux is equal to integration of only E ds, right? So your phi is equal to E will come out of the integration, and then we have only integration of ds. ds means a small part, a small area element of this curved surface area. Now you can say that the entire curved surface area is made up of small elements ds. And you add all those ds, then what will you get?
The total.
ds is a small area element on its curved surface. Okay? Now the entire curved surface of this cylinder can be assumed to be made up of a large number of small area element ds, right? And if you add all those ds, what do you get?
The entire cylinder.
ds is a small area element on the curved surface area. Okay? Now this entire curved surface area can be assumed to be made up of small number of this area element ds. And if you add all those ds, what do you get?
The entire curved surface.
The entire curved surface area. Okay? So here your so I'm going to write this side. Oh, it is a negative one again. So we got phi is equal to surface integration of E ds. This implies your phi is equal to E comes out, and then we'll integrate only ds. Integration of ds means what? Curved surface area of cylinder. Suppose this we have drawn a cylinder of radius r, right? If this cylinder had height h, okay, is of height h, then the curved surface area of the cylinder will be given by 4 pi r square, correct? Yes. And according to Gauss Law, what is your phi? What is your phi? 1 by epsilon naught times
Q.
the charge enclosed. Is it okay? Is equal to E into 4 pi r square, right? Yes. Now, see, we consider that this is an infinitely long straight line charge having linear charge density lambda, right? So according to the definition, linear charge density is given by what? Charge per unit length. Is it okay? Yes. So in that case, here we have assumed, we have taken, this is an infinitely long, but we have taken a certain length of the wire. What is the certain length of the wire? H. So Q upon H. Is it okay? So if you cross multiply, Q will be equal to H lambda. So here 1 by epsilon naught times Q, your Q is H lambda is equal to E times 4 pi r square, right? Okay. Oh my god. It's the curved surface area of the cylinder is 2 pi r h. Oh my god. It's 2 pi r h. Here it is. 2 pi r h. Alright? So here h cancels out. I'm sorry for that. H cancels out. So what do you have? I want to find E. So E will be equal to
2 by RH by.
What are you talking about? E will be equal to here 1 by epsilon naught times lambda is equal to E into 2 pi r. I want to find E. So E will be equal to
1 by epsilon naught lambda
1 by epsilon naught times lambda.
into 2 by r.
How comes into 2 pi r? How comes into 2 pi r? 2 pi r is multiplication with E. So you want to find it, that means you have to transpose this term to the other side. Then
Into 1 by 2 by r.
upon 2 pi r. Is it okay? No? Upon 2 pi r. So this gives you the electric field at any point due to infinitely long straight line charge. Okay? Can you do it? Successful. Now we'll go for the second application of Gauss law. In the first application we studied to find electric field due to an infinitely long straight line charge. This time we will go for electric field due to an infinite plane sheet of charge. Infinite plane sheet of charge. Infinite plane sheet of charge means you have a sheet, okay, carrying charge, okay, and the area of that sheet is like infinitely large, okay. Its area cannot be determined. So what I'm going to do is I am going to draw an infinite plane sheet of charge. So let's say that this is your infinite plane sheet of charge. Okay? This is a sheet. An infinitely long plane sheet of charge. Let's say that also consider an infinite plane sheet of charge having sigma as its surface charge density. Alright? Having sigma as its surface charge density. Now, we want to find out the electric field at any point PC. At any point PC. Okay? So we want to find out the electric field, okay, at any point PC, which is at some distance from the surface of this charge. Is it okay? So in order to do that, we need, what do we need? In order to find out the electric field at this point P, what do we need?
Charge.
We need a Gaussian surface. We need a Gaussian surface, right? So in order to find out the electric field at this point P, we need to draw a Gaussian surface. And this Gaussian surface should be symmetric about the charge. It should be symmetric about this charge. And the electric field at every point on the surface must be same. Electric field must be same. At every point on that surface must be same. Okay? So what I'm going to do is, I have to draw a Gaussian surface. This time also I'm going to draw a cylinder. Is it okay? Such that this point P, this point P lies on the area of cross-section of the cylinder. Alright? That means I have to draw the cylinder in this way. So like this. Is it okay? No? The cylinder, suppose this is your surface. This is your surface. Then this is how you need to draw the cylinder, passing through this like this. Okay, passing through. Alright, your cylinder should pass through this surface. And the point P should lie on the area of cross-section of the cylinder. Are you following that? Okay. I don't have more example. Suppose if this is your surface, it's not circular, but if this is the surface, then you have to draw the cylinder in this way. Okay, so that the point P lies on its, such that the point P lies on the area of cross-section of the cylinder. Is it okay? Yes. Now, now, at point, the electric field due to positively charged is always directed radially outwards. Is it okay? So the electric field at this point P will be in this direction, acting radially outwards. Is it okay? And what will be the area vector of this surface?
Perpendicular.
The area vector of this surface will be perpendicular to this surface. That means it will act along, it will act in the same direction as that of E, right? Yes. The electric field on the curved surface area will be in this direction. Now, the electric field along the curved surface area will be in this direction. Is it okay? And the area vector of this surface will be in this direction. Now, electric field is in this direction, and the area vector is in this, is like this. So that means the area vector for this curved surface area, the area, see, electric field, it's like this, right? Electric field is acting in this direction. Now, and the area vector of this curved surface will be perpendicular to the surface, means area vector is in this direction. So the area vector and the electric field are perpendicular to each other. Angle between them is 90 degrees here. Area vector of this surface will be perpendicular to the surface, and the electric field is acting in this, along this direction. So the angle between them will be 90 degrees. Yeah? For this surface, for this area of cross section, electric field is acting in this direction, and the area vector is also in the same direction. Is it okay? Now you see your area of cross section of the cylinder is like this, right? Now, so the area vector is always perpendicular to the surface outwards, right? And the electric field is also in the same direction, so angle between them will be 0 degree. For this, okay, for this surface also, see, your area vector will always be perpendicular to the surface, right? And your electric field is acting in this direction. Nah? Electric field is in this direction, see. So the electric field and the area vector are acting in the same direction. Is it okay? So the total electric flux over this entire surface will be only due to this and this area of cross section. The electric flux over this curved surface area will be 0. Why? Because the electric field and the area vector are perpendicular to each other. Is it okay? So the electric, so let phi be the total electric flux, okay, over this entire surface. Then the total electric flux over the entire surface will be electric flux due to this surface plus electric flux through this surface plus electric flux through this surface, right? We know that electric flux means E dot integration of E dot ds, integration of E dot ds plus integration of E dot ds. Now you see, for this surface, electric field and the area vector are in the same direction, so angle between them will be 0 degree. So this one will be E ds cos 0 degree. And also for this area too, electric field and the area vector are in the same direction, so it will be E ds cos 0 degree plus for this curved surface area, the electric field and the area vector, they are perpendicular to each other, so E ds cos 90 degree. So the total electric flux will be now equal to
0.
Cos 0 is 1. Cos 0 is 1. So we have E ds plus here also cos 0 is 1. So we have E ds and then cos 90 degrees 0. This is now equal to 0. Okay? So integration of E ds plus integration of E ds 2 times integration of E ds, right? So your phi is equal to 2E into integration of ds. What is integration of ds? ds means a small area on its area of cross section, a small area element on the cross section of the cylinder. So if the entire cross section can be assumed to be made up of small area ds. So if you add all those ds, that will give you the area of cross section of the cylinder. What is the formula for area of cross section of the cylinder? Area of circle by r square. Now the cross sectional area is given by the formula pi r square, right? It's a circle, so pi r square. So what do we have is phi is equal to 2 pi r square times E, right? But according to Gauss law, suppose this is equation 1. According to Gauss law, what do we have? According to Gauss law, the total electric flux over any closed surface is given by 1 by epsilon naught times the charge enclosed. Is it okay? Now, let's say that, okay? So according to, we have assumed that sigma is the surface charge density. Now, sigma is the surface charge density for this sheet. So if sigma is the surface charge density, then we have sigma is equal to Q upon A, charge per unit area. So your Q will be sigma A. So your phi will now become 1 by epsilon naught times into sigma A. Equation number 2. From 1 and 2, if we compare equation 1 and 2, then 2 pi r square times E will be equal to 1 by epsilon naught sigma times A, right? Is it okay? Yes. So in that case, what do we have is, see, pi r square. Pi r square means area of cross section of the cylinder. So pi r square, can we write it as A only? Area. Now pi r square means what? Area of cross section. So pi r square is area, right? A is equal to 1 by epsilon naught into sigma times A. Can we cut A? So your electric field will be given by sigma upon twice of epsilon. So the electric field at any point due to an infinitely long or due to an infinite plane sheet of charge is given by sigma upon 2 epsilon naught, where sigma is the surface charge density of this sheet. Is it okay?